Okay, good morning. This is Professor David J. Delosreyes. Okay, the date for today is December 2, 2023, and the time is 3:22 a.m. Okay, my topic for this session will be AC machines, lesson number 64, and the title will be example problem on the computation of the so-called alternator voltage regulation. Okay, let's proceed. The last time around on lesson number 63, okay, we discussed the concept on how to compute for the armature resistance of alternators, the synchronous impedance for alternators. So if we know the synchronous impedance and the armature resistance, we could compute for the reactance. And if we could compute for the reactance in armature resistance, we could compute for the so-called IR and IX drops for the alternators. So we could actually compute for the so-called voltage at the so-called no-load condition. And if we could compute for the voltage at the so-called no-load condition, we could now compute for the so-called voltage regulation. So the requirement for what they call this voltage regulation is that we must have to compute the armature resistance, the armature impedance, and the armature reactance. Okay, let's proceed. The subject matter for this morning will be AC machines, lesson number 64. The last time around was 63. And the title of the topic for this morning will be example problem on voltage regulation, an application of the so-called concept from the last discussion. Okay, I will try to read the problem. Given an alternator rated 500 kVA, 2300 and 3-phase. This is the alternator. I think, as always, alternator are actually connected as a star connection. I haven't seen what they call this, an alternator that is connected as delta. It's always a Y-connected alternator. So in here, even though the problem doesn't state that the alternator is actually Y-connected, supposed to be, the connection should be Y. I will continue the problem. If the average AC resistance of the three armature winding phases, terminals, equal to capital letter R with subscript T, meaning the terminal resistance, okay, is actually 0.8 ohms. Meaning, if we try to get our ohmmeter here, and we try to measure the resistance between terminals, what comes out is 0.8 ohms. Or this is actually a DC resistance. Okay, it is 0.8 ohms. Calculate the value of capital letter Z with the subscript S, meaning synchronous impedance, and capital letter X with the subscript S, again, synchronous reactance. Assume that the effective AC resistance is 1.5 times the DC resistance. Calculate also the percent regulation for a full load power factor of 0.86 lagging. So at the given condition, if the alternator will try to deliver 500 kVA and the power factor is 0.8 lagging, the problem is asking what will be the percent voltage regulation. Will the alternator could generate a stable voltage? Will it go up or go down during the what they call this transmission of a 500 kVA load with the power factor of 0.8 lagging? The power factor is 0.8 lagging, so supposed to be, we assume that all the loads are actually motor loads, and it is actually the worst condition for an alternator to deliver current to motor loads. That's why during peak hours, okay, utility companies try to convince us to shut down our air conditioners because the alternators from the generator side might be overloaded, including the transmission lines. Okay, let's proceed. For the figure, like what I said, it was not stated that the alternator was Y connected, so we assume that the connection will be Y. So this should be the figure. This is the windings per phase. The measured resistance between terminals is 0.8 ohms. Okay. The problem is asking what will be capital letter C with the subscript S synchronous impedance. What will be capital letter X with the subscript S meaning synchronous reactance. And what will be the percent regulation with the given condition. The power factor is 0.8 lagging. 0.8 lagging meaning the voltage and current are actually, or the current lags the phase voltage by an angle theta, okay, and which is to be computed by taking the arc cosine of 0.8 here. Later on we could compute what will be the, what you call this, angle of lag. That's an easy one. It will just be simply an arc cosine of the given power factor, which is it is 36.9 degrees. So if this is the current, this is the voltage, the angle separating the current and the phase voltage is 36.9 degrees. Oh, that's the meaning of 0.8 lagging. Okay, let's try to bring out the given. The total apparent power of the alternator is 500 kVA. That should be the output, the rated output. It is three-phase. First phase, second phase, third phase. It's three-phase. The given voltage 2300 is supposed to be a line-to-line voltage. When they give specifications on the voltage for alternators, it is not the phase voltage. It's always the line-to-line voltage. Okay. So I place it here, capital letter B with the subscript L, meaning the line-to-line voltage is 2300. So this is 2300 volts. Right? 2300, this is 2300, it's balanced, it's an alternator. Okay, let's try to bring out the solution now. The first part of the solution process will be to compute for the voltage per phase. We are given the line-to-line voltage here, BL equal to 3300, right? So if the line-to-line voltage is given, we could compute for the phase voltage here. Okay, and the relationship of the line-to-line and phase voltage for a Y-connected alternator or transformer is given by the voltage per phase should be the, what I call this, the line-to-line voltage over square root of 3. The relationship is B line-to-line is square root of 3 times voltage per phase. It is given by this equation here. So we are given the line-to-line voltage, we could compute for the phase voltage. So it's letter B or letter H the same. But since we are talking alternator here, E refers to the so-called generated voltage. So the generated voltage per phase will be the given line-to-line voltage over square root of 3. This is 2300 over square root of 3, and this is 1330 volts. So in here, what will come out will be 1300. This is 1300. This is 1300. Okay? Oh, what's next? In the computation of the so-called synchronous impedance, the formula will be this. Okay, it will be the open circuit voltage per phase divided by the short circuit current. We know this. That's during the performance of the open circuit test for an alternator. And how about the short circuit current? For the short circuit current, we don't know yet for the time being, but if we try to bring out the solution, for the given alternator, there should be the so-called short circuit test, okay, which gives the relation of the field current, the excitation current, and the short circuit current. And I am telling you now, for this problem, the short circuit current is 204 amperes. Okay, it was not given from the problem, but if we try to, actually there was a graph for this problem, and if we try to look back on the graph of the so-called short circuit test, which involves the field current, excitation current, and the short circuit current. Okay, for this alternator, the short circuit current is 204. The short circuit test line is actually a straight line. So at this given IF, if we try to draw a vertical line, it intersects the short circuit test line. Okay, and if we try to draw what we call this horizontal line, this horizontal line refers to the so-called short circuit current. It's 204 amperes. So actually we know 200, that's why I place it here from the curve. Okay, okay, the capital letter I with the subscript is C, meaning the short circuit current is 204 amperes. This is needed in the computation of the synchronous impedance. Okay, so if we now know what they call this, the open circuit voltage. How about the open circuit voltage per phase? If there is no load, right? And if we try to compute for the open circuit voltage, what will come out will be 1,300, right? There's no load. So if the line to line is 2,300, the voltage per phase of the open circuit will be 1,330. So this open circuit voltage is actually the voltage per phase. So this should be 1,330 over 204. This 204, don't ask me this one now, it came from the curve, right? Right? This is at 204 amperes. This one. So 1,330 divided by 204, that will be 6.52 ohms per phase. Okay? Meaning the synchronous impedance per phase is 6.52, 6.52, 6.52. Synchronous impedance, it's a vectorial addition of reactance and armature resistance. So this is actually the total. So it seems we are now on AC circuit, right? Like what I said before, our knowledge under AC circuit will be applicable to transformer and alternator. That is, the impedance is actually the vectorial sum of the resistance. X of S is actually an imaginary part plus Jx of S. Okay? And for how about the armature resistance? We could now determine the armature resistance because according to the problem, the DC resistance between terminals is 0.8. Okay? And how many windings are involved between two terminals? There are two windings, right? If we measure 0.8 here, this 0.8 refers to the resistance of this plus this. So since this is balanced, the resistance per phase will be 0.8 over 2, if this is 0.8. So actually, if we try to take the value of RA, the effective armature resistance, okay, it was given that it is 1.5 times the measured value here. So it should be 1.5. The DC resistance per phase is 0.8 over 2, right? It's 1/2 the line to line. So what will come out will be 0.6 ohms. This is a very small value, right? Meaning to say the given alternator was actually wired with the good copper wire maybe. That's why the armature resistance is very small, it's 0.6 ohms. We needed a small RA such that the voltage regulation will be not high, but it still come out to be high. How could we compute for the value of X of S now? Oh, just go back to your vector diagram. We now know RA, we now know ZS, so we could compute for this. Okay, we use Pythagoras principle. This is a right triangle. Hypotenuse is given, the adjacent side is given, we could compute for X of S. So the absolute value of x of s, absolute value, just the magnitude, will be the square of this minus the square of 0.6. Since this 0.6 is small compared to 6.52, what will come out for x of s will be 6.5 ohms per phase. Okay? Let's try to bring out the so-called percent regulation. For the percent regulation, it is actually the voltage per phase at no load minus the voltage per phase at full load over at full load times 100%. So this is actually the voltage per phase at no load or at full load, right? And at no load, we must have to add up this value here plus this value. E with the subscript X, meaning the drop due to the synchronous reactance, and E with the subscript R is actually the voltage drop due to the armature resistance. We will add this one here plus this to the vectorial value of voltage per phase to get this one. But the voltage per phase at no load got an angle of 36.9 degrees, so it got two components also. This is the vertical component and this is the horizontal component. Okay, this voltage per phase at full load, it got a horizontal component and vertical component, right? So if we now try to segregate this one, we could erase this one now because we got the components already. This part here is this one, and this part here, this portion is this one. Okay, and this portion is actually what you call this? No. This one should be this. This one is for the R, right? This is the IR drop of the armature. This is the horizontal component of the voltage at per phase at no load. This is the vertical component of the no load per phase voltage. And this is the drop due to the reactance of the armature, right? So for the real part, there are two voltages. Okay? The real part will be this one here, 1330 times 0.8. The horizontal component of this, plus the value ER. ER is actually 75.4. Real part, what will come out will be 1139.4 volts. Am I still in camera? And the imaginary part, the vertical thing, will be this part here. Okay, this is actually voltage per phase sine of theta. This is 1300 times 0.6. Okay, this part here. Plus this EX here, which is actually 817. This is 817. So 1300 times 0.6 plus 817 is 1615 volts. So considering the real part and imaginary part, they are big. Okay? Why they are big? It is something like this. Okay, I will try to erase this one. It's big. I will now try to erase this one. These should be the resulting voltages after this, taking the summation. The real part is 1139.4 and the imaginary part is plus J 1615. Okay? Imaginary part of the, and the vectorial sum is, this is actually the voltage per phase at subscript no load. Okay, it's a very big one. So if we try to compute for this, this is the one needed in the computation of the voltage regulation. It will be the square of this plus the square of this, then take the square root. It is this. Right? What will come out is 1937 volts. There was a big, what you call this, voltage drop. Because at full load, it's only 1330. And at no load, it should produce 600 volts more because this is 1937, right? So if we now try to compute for the percent voltage regulation, this is no load minus full load over full load times 100. It is 45.7%. This is high. Okay. The alternator got what they call this a parameter which give us a big voltage drop. That's why the percent regulation is very high, 45.7%. That's understandably what they call this expected, because alternator is actually a moving machine, right? For the transformer, the percent voltage regulation is actually very low because what they call this transformer got no moving parts except for the moving parts. But for alternators, there is a physical, what they call this, movement of the alternator just to generate voltage. That's why the percent voltage regulation is high. Okay, good morning from Los Angeles. This is Professor David J. Delos Reyes.